In this tutorial, we are going to talk about tactile switches. Tactile switches are very useful in many electronic applications and hardware projects. So let us go ahead and check what do we need in terms of hardware components for this tutorial. First of all, we need an Arduino Uno R3, some fixed value resistors, tactile switches, a battery or a power source, a breadboard to assemble our circuit, along with some wires and a USB cable to connect our Arduino Uno to our PC or laptop. So, what's a tactile switch? A tactile switch, or for short tact switch, is an on-off electronic switch that is only on when pressure is put on it, or when it is pressed. As soon as the tactile switch button is released and the pressure has been released, the circuit is then broken. So let us look at what we have right here in front of us. We have an Arduino Uno, and on our breadboard we have the tactile switch right here. So let us see how it works. If I want to activate this tactile switch, what I want to do is just press on it and keep this pressure applied. As soon as the pressure is released, the tactile switch goes off. And we will fully understand in this tutorial how to design a proper circuit for this tactile switch to operate properly, and how can we program it using LabVIEW Community Edition. So tactile switches provide a simple way for users to interact with a physical system and are found in most electronic devices such as the power button on your smartphone or laptop. Now let us look at the internal structure of a tactile switch. So this is the tactile switch that we have just seen in front of us, and this is its schematic diagram. As we can see, a tactile switch typically has 4 pins. However, essentially it has only 2 terminals. Since pin 1 and pin 2 here are connected internally, and pin 3 and pin 4 are also connected internally. In other words, pin 1 and pin 2 constitute one branch, and pin 3 and pin 4 they constitute another branch. Now, when pressure is not applied on the yellow button right here, the circuit is open, or the tactile switch is in an open position. However, when pressure is applied on the yellow button, the tactile switch is closed, and current can flow from branch 1 connecting pin 1 and pin 2 to branch 2 connecting pin 3 and pin 4. Now, there's a very important note right here. There's usually a confusion between what's a tactile switch and what's a push button. And usually these two words are used for the same element. However, there's a major difference between a tactile switch and a push button. For a tactile switch, as we said right here, we need to apply a pressure on it, keep the pressure, and then once the pressure is released, the tactile switch goes off. However, a push button works a little bit differently. For a push button, we press it once, it's activated, and then to deactivate it, what we need to do is to press again in order to disengage it. So this is the major difference between a push button and a tactile switch, and we need to be aware of this difference. Now, tactile switches, they come in different colors, sizes, and shapes. And you can choose the color, size, and shape depending on your desired application. And sometimes you can use these caps right here in different colors as well in order to make them look more fancy or more proper in your product or device. Now, before we hop into digging deep into what's a tactile switch and how does it work with an Arduino and LabVIEW, first what we need to understand is how the digital pin on the Arduino Uno or any microcontroller works. Now we know that in the digital world we have either 0 volts or 5 volts. In other words, we're talking about binary, 0 or 1. Whenever we say we have binary 0, it means that we have 0 volts. And whenever we say that we have binary 1, it means we have 5 volts. Why is that? Because the digital world is based on transistors, which we will discuss in our future tutorials. And transistors, think of them right now as switches, just on-off switches. So we can turn a circuit on or off using these switches. When the circuit is off, we have 0 volts, and this is represented by binary 0. And when the switch is on, which is the transistor, we have 5 volts, and this is represented by binary 1. Now, whenever we say we have binary 1 or 5 volts, which means the switch is on or closed, this is represented by digital high. Similarly, whenever we have 0 volts or binary 0, which means that the switch is off, this is represented by digital low on our digital pin. So whenever we say we have digital high, it means we have a 5 volts logic signal. Whenever we say that we have digital low, it means we have 0 volt digital signal. Perfect. Now, whenever we talk about microcontrollers, we talk about transistor-to-transistor logic. And this means that on our Arduino Uno right here, we have different digital pins. So on the Arduino Uno, we have 13 digital pins. And these digital pins, they can be configured either as digital inputs, which means they accept a signal, and based on the magnitude of the voltage of the input signal, we will have either digital high or digital low, or they can be configured as digital output pins, which means we can send signals either 0 or 5 volts out from our digital pins. However, for a microcontroller to consider a signal as a digital high or a digital low, some ranges must be respected. And let's look at these ranges. For example, for the standard 5 volts TTL, transistor to transistor logic levels, for the ATmega328, which is the microcontroller on our Arduino Uno. So if you look at our Arduino Uno right here, we can see the ATmeg right here, 328. And this is the microcontroller that is placed, or that is the brain of our Arduino Uno. Now for this one, we have these voltages right here in front of us. So the first one is VCC, which is the upper voltage, 5 volts, and the second one is the ground, which is represented by 0 volts. And we have 4 other different voltages. Let's go over them to fully understand them and fully understand what they mean and how to abide by these ranges in order to have a reliable digital high or digital low signal whenever we're reading or sending digital signals. So VOH, it's the minimum output voltage level a TLL device will provide for a high signal. In other words, what we mean by VOH, this 4.2 volts, when we configure a digital pin as a digital output pin and we send a digital signal out of the Arduino, the minimum voltage that will be sent by the Arduino pin is 4.2 volts. Now, similarly, what's VIH? Let's look at it. Minimum input voltage level to be considered a high. Now, whenever we configure a digital pin on our Arduino Uno to be as a digital input pin, which means it's accepting a signal, the minimum voltage that will trigger a digital high is 3 volts. So if the voltage is above 3 volts, the Arduino Uno will be able to trigger a digital high, or the digital pin will be able to read reliably a digital high signal. However, if the voltage is below 3 volts, let's say between 1.5 and 3 volts, we will have a floating voltage or a floating state, which means the Arduino Uno won't be able to determine reliably whether the signal is low or high. Now, what's VOL? VOL, the maximum output voltage level a device will provide for a low signal. When a digital pin is configured as a digital output signal and we send a digital low signal, the maximum output voltage that will be sent is VOL, which is 0.9 volts. Finally, VIL, the maximum input voltage level to still be considered a low. Now, when we configure a digital pin on the Arduino Uno as a digital input pin, which means the Arduino is accepting a signal through this pin, the voltage must be below 1.5 volts right here in order for the Arduino to reliably interpret it as a digital low signal, which means binary 0. Now, what we are interested here in right here is VIH, which is 3 volts, and IL, which is 1.5 volts, because for our switch right here, let's go back to our circuit. For our switch, we want to trigger either digital high or digital low, depending on whether we're pressing or not pressing our tactile switch, because we need to configure one of our digital pins right here as a digital input pin. And we will read either digital high or low based on whether we're pressing or not pressing our push button. Now, or tactile switch. Now, what we need to make sure is that whenever we want a digital high, the signal must be above 4.2 volts. And whenever we want a digital low, or to trigger a digital low, the voltage must be below 1.5 volts. So let us go ahead and write these two statements right here in order to keep them in front of us, because later on we will design the circuit for our tactile switch. So we have V. Let's get back to our slides. So we have VOH and VIH and VIL. So not VOH, but VIH. So VIH is greater than 3 volts. So let's double check it. So it's the minimum voltage level to be considered as a high, and VIL is the maximum input voltage to be considered as low. So VIH is equal to 3 volts. So 3 volts. And our input voltage, let's say, from the tact switch, let's write it this way, must be greater than 3 volts to be considered digital high. Now, for V, let's go back and check it together. For VIL, which is 1.5 volts, the input voltage from the tact switch must be less than 1.5 volts to have digital low. Now, these two threshold values are very important because we need to have a reliable operation by our tact switch. Perfect. Now let us go ahead and look at a simple circuit for our tact switch and how we can design a proper circuit for it in order for it to operate reliably between digital low and digital high. Now, whenever we have a microcontroller, and suppose that nothing is connected to our digital input pin, usually the voltage that will be read by the pin if nothing is connected to it is called a floating voltage, which is a random voltage. And what will happen in practice, as we will see later on, that the pin will be floating between or randomly switching between digital high and digital low. And we call this a floating pin because we don't have a state that is clearly defined as digital high or digital low, since the pin is switching randomly between these two states. Now what we can do is we can pull our digital pin right here on the microcontroller, we can pull it to the ground. And by saying that, what we mean is that we can connect our digital pin directly to the ground, and this way now the digital pin will read 0 volts and consequently it will read digital low. Or we can read through our program digital low. Now what we can do is, between the digital pin and the ground, we can place a tactile switch. And this tactile switch can be in two different positions. Either it can be an open switch, or we can close it by simply pressing on it. Now if we close the switch, let's think about it. So let's just illustrate it right here. We have our microcontroller right here. So this is our microcontroller. And this is our digital pin right here. So digital input pin, I will call it. Now what we can do is we can connect this digital pin directly to the ground right here. And now this is called pulling down our digital pin. So it's pulling down the digital pin to ground. And in this case, what we will read is digital low. Now let's say what we want to do is we want to right here place a switch, a tact switch. So what we can do is we can place a tact switch right here. And this stacked switch can be in two different positions. Either it can be an open switch or a closed switch. Let's close the switch first. So if I close the switch, let's say I have a closed switch right here. So closed switch. What do you think will happen? So what will happen eventually right here is that we're pulling down our digital pin, and so closed switch, what will happen is we will read digital low. Now what happens if we open the switch? If we have an open switch, for short OS. So open switch. If we open the switch, what will happen is the following. Let's think about it together. So let me delete these two and open the switch for you to see it clearly. So this is the switch right here, and it's in an open position. So instead of closed, open position. Now what will happen is that the digital pin will be in a random state. In other words, it will be switching randomly between digital high and digital low. Why? Because we don't have a clearly defined voltage across this pin that can be read. We need either a voltage that is close to 5 volts or greater than 3 volts in order to read digital high, or a voltage that is lower than 1.5 volts in order to read digital low. However, we know that in the surrounding environment, what we have is electromagnetic interference, or EMI, electromagnetic radiation, and due to electromagnetic interference, this pin right here will pick up any noise from the environment, and it will be switching between digital low and digital high. In other words, it will be operating unreliably. We won't have a reliable operation. Now, when the close is switched, we know that it's pulled down to the ground, but when the switch is open, we have a problem. Now, we can overcome this problem using one technique, which is pulling the digital input pin high when the switch is open. How can we pull it high? It's very simple. Let's look at it. In order to make sure that we read one state when the switch is open, we can pull it high. To pull it high, this is what we do. Okay, let me delete this thing right here. So I can, for example, on the 5 volts voltage source on the Arduino, connect my digital pin when the switch is open. So I will connect my digital pin right here to 5 volts when the switch is open. In this case, we say that we're pulling the digital input pin, we're pulling it high. And in this case, when the switch is open, we will read digital high. However, let's look at one major problem right here. And what will happen in this case? When we close the switch. Suppose now we want to close the switch. So let's close the switch. So now I have the switch closed right here. If we close the switch, let's look at what will happen. Current will flow right here through the digital pin, and part of it will flow through the tactile switch. Now I have plus right here, I have minus right here, and simply what will happen is what we call a short circuit. And you should never do that. You should never pull your digital input pin or digital output pin high, all right, without in this fashion. In other words, without a resistor. So how can we fix this problem? How can we fix this short circuit problem and avoid burning our Arduino and circuit? It's super simple. What we can do is, let's look at it together. We can add right here you should guess a resistor, and this is called RPU, and RPU stands for pull-up resistor. What does it mean, pull-up resistor? It means that for our pull-up resistor, it means that if the switch is open, our digital input pin will be pulled high because this resistor will be chosen so that the voltage read by the digital input pin when the switch is open, it will be greater than 3 volts and we will read digital high. And whenever the switch is closed, some current will flow through this resistor, so it will control how much power is dissipated, and we will avoid having a short circuit, and we will read digital low. Perfect. So now, This is a pull-up resistor, and we will look at how can we design properly a pull-up resistor in this tutorial, and we will also look at pull-down resistors as well. Now that we have fully understood how should we connect a tact switch to an Arduino Uno or any microcontroller. So let us look. So pull-up resistor design. How do we design a pull-up resistor? In other words, how do we choose the value right here of this resistor in order to have a proper operation? So let us go through the design procedure, fully understand the circuit of a pull-up resistor and a pull-down resistor, and then we'll start with coding. Design procedure. The value of the pull-up resistor must be selected to satisfy two main conditions. The first condition, when the tactile switch is pressed right here, so when the tactile switch is pressed right here, the input digital pin is pulled low, as we said in our previous example right here. Whenever it's pressed, we need our input pin to be pulled low. And in this case, the magnitude here of the pull-up resistor will control how much voltage or the magnitude of the voltage read by the digital input pin, as we will see in a bit. So resistor R1 controls how much current or power do you want to flow from Vs through the button and then to the ground. So whenever the switch is pressed, some current will flow through the tact switch right here to the ground. And in this case, it will control how much power will be dissipated right here. And usually we want to minimize this amount of power. Now, when the tactile switch is not pressed, the input pin is pulled high. What do you mean by that? So right here, the switch is open. And you know that the input pin will be pulled high. In this case, the value of the pull-up resistor controls the voltage of the input pin. I guess I have said it in the opposite fashion. So this is what we need, these two cases. So here, when the tactile switch is not pressed, the input pin is pulled high, and the value of the pull-up resistor controls the voltage that will be read. And usually this voltage, we need it to be greater than 3 volts. So we need to design our tact switch in such a way that this voltage is above 3 volts to read reliably digital high. And when the tact switch is closed, we need to control the amount of power and also to make sure that our digital pin is pulled low. Now let us go ahead and see or look at how we can do that. Perfect. Now, before we hop to our notes, let's look at our microcontroller right here. Every digital pin or a microcontroller has what we call an input impedance. Now, what do you mean by an input impedance? It's an equivalent resistance value. And think about it here. We can model it as a single resistor. So every microcontroller has an input impedance with a certain value. And in order to properly design our pull-up resistor value, what we need to do is we need to go to the data sheet of the microcontroller and get the exact values of the input impedance to be able to design our pull-up resistor value or pull-down resistor. Perfect. So let us go ahead and to our notes. So now let us talk about pull-up resistors. Let's first of all start with the case of pull-up resistors. So right here we're going to pull-up resistor design. So pull-up resistor design. So what we have for our pull-up resistor, I will draw the circuit a little slightly differently for you to be able to fully understand what's going on. So it will make it easier. So we have our tactile switch that is pulled high. So here we have RPU, and between this resistor and the ground we have our tact switch. So this is our ground node right here, and in parallel we have the input impedance right here, RI, I will call it RI, R input impedance for the digital input pin, and this is the voltage that we're reading right here. We call it VI or VI, since these two, the tact switch and the resistor, input impedance resistor, are in parallel. Now what we need to do, we need to check for the two cases right here. When the tact switch is open, what will happen, and when the tact switch is closed, also what will happen, and how to design RPU accordingly. Now case 1, tact switch or tactile switch is open. And in this case, we expect to read digital high. To do so, to read digital high reliably, our voltage must be greater than 3 volts. So, if our tactile switch is open, what do we have? It means this branch right here, it's as if it's not there. We have an open circuit. So what I have right here, I have a voltage source, Vs equals to 5 volts, and in series with this voltage source, we have two resistors, RPU and RI. So simply what we have is a voltage divider circuit, and we have discussed this circuit in details in our previous tutorials. So please go ahead if you're not familiar with the voltage divider circuit and watch the previous tutorials. So what we have right here, what we can write is that VI, the output voltage, is equal to RI over RPU plus RI times Vs. Now we know in this case that Vs is equal to 5 volts and RPI or RI, the input impedance, usually it's a fixed value that we can get from the datasheet of the microcontroller, in this case for the Arduino. Now, let us say that the R input is 100 kilo ohms, and usually it can be between tens of ohms, of kilo ohms, excuse me, to it can go to the order of mega ohms. It depends on the microcontroller. That's why you need to go to the data sheet in order to find it. Now let's say for this example, it's 100 kilo ohms, the input impedance. Now we know that this value is fixed and Vs is fixed. So we know that Vi, when the switch is open, is controlled by the magnitude of RPU. Now think about it. If we want Vi to be really close to 5 volts, in other words, to be above 3 volts, for our digital input pin to read digital high reliably, what should we do with RPU compared to Ri? Should it be smaller or larger? In this case, we can see that we need this fraction to convert to 1 or converge to 1. And for that reason, what we need is we need RPU to be smaller than Ri, much smaller than Ri. Now how smaller? Usually the rule is that Ri over RPU must be equal to 10, so by a factor of 10. In this case, we can deduce that RPU is Ri over 10, and in this case, it's equal to 100 over 10, and it's equal to 10 kilo ohms. Perfect. So this is why you have seen right here that the pull-up resistor value is set to 10 kilo ohms for this reason. And let's see why this is the right choice for this pull-up resistor in this scenario. Because now we can compute Vi. Let's see what's Vi when the tactile switch is open. Vi is equal to Ri, which is 100, over RPU, which is 10, plus 100 times Vs, which is 5. And in this case, what we will get is 4.545 volts. And this voltage is greater than 3 volts, so we will read reliably digital high. Because we know that for the TTL levels, the voltage must be V right here. VIH must be greater than 3 volts to read reliably digital high by the digital input pin, and the voltage right here is 4.545 volts, which is way greater than 3 volts, which is pretty close in fact to 5 volts. Perfect. Now let us look at the case when the switch is closed. So case 2, switch or tactile switch is closed. Let us look at what will happen right here. So if the tactile switch is closed right here, let's draw the circuit again to fully understand what's happening. So we have plus minus 5 volts. We have RPU right here. We have the switch is closed, and we will assume that the resistance of the switch is quite small, 10 ohms in this case, when it is closed. Ideally, we could say that it's 0 ohms, but in practice, it's not 0 ohms. It will never be 0 ohms. And we have RPU right here, which is equal to 100 kilo ohms. Now, if we say that for example, if RS is 0 ohms, we know right here that we will have a wire and we'll have a short circuit, and the voltage right here, VI, will be simply 0 volts, and we will read digital low. But in practice, this is the ideal case. However, in practice, RS has some resistance, okay? Or the tactile switch has some resistance. It's made of a metal at the end of the day, and any metal has some resistance, some sort of resistance. So here we're assuming that it's pretty small. Now what we need to do is to find what's VI, what's the voltage that will be read by the digital input pin. Let's look at it. So first of all, we see that here we have two resistors in parallel. So what we can do is we can get the equivalent resistance. So let's call it R equivalent. It's 1 over RS plus 1 over R. So this is not RPU, this is RI, 1 over RI. And in this case, we'll get 1 over 10 times 10 power minus 3 to convert from ohms to kilo ohms, plus 1 over 100 kilo ohms. And in this case, we'll get 9.99 ohms for our equivalent resistance. So now we can redraw our circuit. We have VS, we have RPU, and we have R equivalent right here. And right here we have the ground pin. Perfect. Now this is the VI that we are interested in, the voltage that will be read by our digital input pin. Again, we have a voltage divider. So VI is equal to R equivalent over RPU plus R equivalent times VS, right? Now what we can do, we can write 9.99 over RPU, which is 10 times 10 power 3 to convert from kilo ohms to ohms, plus 9.99 times 5 volts. We need to make sure we have consistency in terms of units. In this word, now VIP or VI, the input voltage, is 0.00499 volts. And we can see that it's much smaller than 1.5 volts, which is the voltage that is required, or the threshold voltage for our digital input pin to read reliably digital low. So it's quite low, and in this case we'll read digital, our microcontroller will read digital low. Perfect. So now we know that whenever we have a pull-up resistor, right here, whenever we have a pull-up resistor, which is the case right here, if the switch is not pressed, we'll read digital high. So it's quite opposite to what's intuitive. And if we press on the tactile switch or activated, we will read digital low. Now, this is for the pull-up resistor. Now this 10 kilo ohms value, so RPU right here, RPU, which is equal to 10 kilo ohms, make sure that we read digital high when the tact switch is open and digital low when the tact switch is closed. However, what we need to take also into consideration, because remember we have two conditions. We have when the tactile switch is not pressed, the input pin is pulled high. The value of the pull-up resistor controls the voltage of the input digital pin, and that's what we demonstrated right here. So right here, when the tactile switch is open, right here is not pressed, the RPU dictates how much voltage is read by the digital pin. And in this case, we needed higher than 3 volts in order to make sure we read digital high. However, when the tactile switch is pressed, which is case 2, the input digital pin is pulled low in this case, and it controls how much current flows through this resistor. So it controls the power. So let us compute the power right here when the tactile switch is closed. So when the tactile switch is closed, we need to make sure how much current is flowing right here, because we need to, in most cases, to minimize this current and to minimize the power consumption, especially if we have a circuit with a battery, for example. We need our battery to last long for a certain operation. In order to do so, we know that the power for our pull-up resistor, the power of the pull-up resistor, okay, PUP is equal to simply the voltage across this resistor times the current I flowing through the resistor. And this is our circuit right here. We have computed VI right here, and we said that we found that VI is equal to 0.00499 volts. Now we can find VPU by simply applying KVL. So we know that VPU will be simply Vs minus VI. It will be equal to 5 minus 0.00499 volts. And here what we will get roughly is 4.995 volts. So this is the voltage the voltage across our pull-up resistor. Now we need the value of the current. The value of the current, we can find it right here from the circuit that contains the equivalent resistance. So I is equal to simply Ohm's law. So Ohm's law, I is equal to Vs over Rpu plus R equivalent. In this case, we have 5 volts over Rpu, which is 10 times 10 power 3, plus R equivalent, which is 9.99 ohms. And in this case, we'll get a current value of 0.000499 amperes. Now, we have the current flowing through the pull-up resistor and the voltage across it. We can compute the power. So the power of the pull-up is equal to 4.995 times 0.00499. And what we get is 2.498 milliwatt. So here I'm just doing some approximations and conversions in terms of the numbers. All right, so this is all fine. And this is the power. So it's 2.roughly 5 milliwatts. If we need a lower power, what we need to do is we need to play with the magnitude of our pull-up resistor. This is why we call a, so let's see it, we call a low resistor value a strong pull-up, since it draws more current. In other words, if we have a lower value right here for our pull-up resistor, we know that more current will flow, and this is called a strong pull-up. However, a high resistor value is called a weak pull-up, since less current can flow and we can minimize the power. However, when the high resistor, we need to make sure that the resistor value is not very high, because it will violate the condition right here, the condition of making sure that we will read digital high. Since if RPU is way larger, okay, it's very large, this fraction right here will be will lead to a VI that is lower than 3 volts. So we need to make sure that we design our pull-up resistor in a way that it does not violate these two conditions. So it needs to abide by these two conditions to make sure we have a reliable circuit that gives us digital low and digital high reliably whenever the tactile switch is not pressed and pressed respectively, and to minimize our power consumption. Perfect. Now, let us look at a pull-up resistor, a pull-down resistor circuit. Now, for the pull-down, it works exactly in the same manner, but the catch here is that when the tactile switch is open, we will read digital low, and when the tactile switch is closed, we will read digital high. Let us look quickly at the circuit to fully understand. So we can see right here for the pull-up resistor, it's connected between the 5-volt source and the digital pin. For the pull-down resistor, it's connected between the ground and the junction here that is connecting our digital pin to the tag switch. So they just set the pull-up resistor and the resistor, whether it's pull-down or pull-up, and the switch, they just switch their place, as you can see. So this is the circuit for the pull-down resistor. Let's analyze it quickly, since we fully understood the pull-up resistors. So pull-down resistor, and usually pull-up resistors are more common than pull-down resistors. So here's the circuit. So we have Vs, which is 5 volts right here. We have our tact switch right here. We have our PD, our pull down. We have right here our input impedance, which is 100 kilo ohms, and we have right here RS. So let us analyze the circuit. Now case 1, again, switch is open. So if the switch is open, what do we expect? Let's look at it. If the switch is open, we have no current flowing right here. There is no current absolutely whatsoever flowing right here. So the current flowing through IPD is 0 and the current flowing through RI is 0. And simply what we will read is 0 volts. In this case, we will read digital low. And for a pull-down resistor, it's more intuitive in terms of the operation, because if the switch is not pressed, we will read digital low. If the switch is pressed, we will read digital high. So it seems more intuitive. However, we can flip for a pull-up resistor, we can flip whether we read digital high and digital low programmatically in LabVIEW, as we will see later on. Now, case 2. For case 2, switch is closed. If the switch is closed right here, let's close the switch. So this will be our circuit. VS. We have RS, which is 10 ohms again. We have RPD. We have the ground pin right here. And right here we have RI. Now again, what we have right here is a circuit, and we need to find VI right here, that will be red. So as you can see, we have two parallel resistors right here, and we can find R equivalent. So R equivalent is 1 over RPD plus 1 over RI, and here we have 1 over RPD, which is 10 times 10 power 3, or we can do the opposite, plus 1 over, so actually, they are both in kilo ohms right here. So 1 over 10 plus 1 over 100. And we get 9.09 kilo ohms. Perfect. Now, in this case, VI is equal to, we have a voltage divider circuit. We have R equivalent over RS plus R equivalent, since this will be our new circuit. So let's redraw it here. So VS, RS, and R equivalent for the switch, and this is the ground right here, times VS. So in this case, VI is equal to R equivalent, which is 9.09 over the R of the switch, 10 times 10 power minus 3 to convert from ohms to kilo ohms, plus 9.09 times 5 volts. And in this case, the voltage is 4.995 volts, greater than 3 volts, and in this case, we will read digital high. Perfect, and this is it for a pull-down resistor. So now we have fully understand what's a tactile switch, how to design a pull-up or pull-down resistor for our tactile switch in order to make sure that we reliably read digital high and digital low, depending on the type of the resistor used, whether pull-up or pull-down, and how to minimize the power consumption whenever current is flowing through this resistor, and in other words, when the tactile switch is activated. Now what we are going to do next, we are going to look at the circuit. So this is the circuit that we have in front of us, and in this tutorial we are going to use a pull-up resistor for programming. Perfect. So we have the circuit right here, the pull-up resistor. So we're using a 10 kilo ohms resistor with the Arduino Uno, and this is the circuit right here. You can replicate it in order to write your Arduino or your LabVIEW code. So let us now go to LabVIEW and start coding to see everything in action. So this is the circuit also right here. So I'll go to File, Open, and I have already a new VI created for me right here. I'm gonna place my block diagram and my front panel side by side. Perfect. Now what we want to do, so actually let's maximize our block diagram. What we want to do is we want to read a digital input. So as usual, we can start by building our code. So we need a stop button for our while loop right here. We can hide its label. It will look nicer. So we can place it right there. We also need to always place a timer right here in order to make our code more efficient. So let's put in here 10 milliseconds. Then we go to the Hobbyist toolkit. We pin it right here. We need to open the connection, close the connection, and for the peripherals, we need a digital read block. Since we want to read the digital, input or the digital state of our pin. Perfect. So let us place them. Now we can connect these blocks. And in case we have an error message, we need to contain this one. So we can go to Dialog and Interfaces, General Error Handler, place it right there. And for our serial port, for me it's COM3, for you it might be different. So that's totally fine. Now what we need to do is to define the digital input pin. Our digital input pin in this case is connected, or our wire right here between our 10 kilo ohms resistor and the tact switch is connected to digital pin 7. So we'll specify right here digital pin 7. And finally, right here we can read the value. Now let us go ahead and look at what we can read. So let us just grab here an LED and say tact, call it tact or tact switch status perfect, or tactile switch, tact switch status. All right, now let us put this one right here. And we need one more thing. In case we have an error, we need to make sure that we stop the code, either using the stop button or if we have an error. So for that, we need to unbundle the error right here and connect it to the OR gate right there. And we need to always make sure that our code is neat and readable. Perfect. Now what we can do is, I can minimize this one, place our Arduino on one side and our front panel on the other side, and run the code. So as we can see right here, now the pull-up resistor, or the tact switch is not pressed. What does that mean? It means we're pulling high the digital pin, and as you can see, the LED here is on, the virtual LED, which means we're pulling high our digital pin. As soon as we press our tactile switch, our digital pin is pulled low, and this tact switch or circuit or the resistor seems to work pretty fine, because we can see that we have clearly two defined states and the digital pin is not floating or randomly switching between digital high and digital low. Now let us do one thing right here. Let us remove the 5 volts right here wire. And now we have the switch connected between the ground and the digital pin. And let me approach it with my finger right here. So as you can see now, it's pulled low. It's not working properly. And now as soon as I approach it with my finger, look at it. Due to the static electric field right here with my finger, it's randomly switching between digital low and digital high. So we can clearly see an unreliable operation. If I approach it with my phone, the same thing will happen due to electromagnetic interference. So as soon as I pull it high right here, I can make sure that whenever the switch is not pressed, our digital pin is pulled high. Perfect. Now what we are going to do next is to count the number of clicks. So how can we know how many times did we click our tact switch? But before that, what we need to do is we need to invert its operation. In case you want to make it more intuitive, what you can do here programmatically in LabVIEW, we can go to the Boolean, choose the not operator in order to flip the input. And now if we run the code, we can see clearly that if the tact switch is not pressed, we will read digital low. Now when we press it, we will read digital high. So now it looks like a more intuitive operation, at least for the user. Perfect. Now what we want to do, we want to count how many times the push button or the tact switch is clicked. Again, you should not use a push button for a tactile switch, this keyword. However, when I say push button right here, what I mean is this yellow button and not the tact switch. We should say the yellow button and not the push button to be more accurate. Perfect. So let us look at something. So we can go to structures, case structures, and here what we can say is create a shift register right here, and we can initialize this shift register. So if we want to count, we want an integer right here. And for this shift register, we will say if the tact switch is not pressed, so let us move these a little bit backward, and let us place our case structure right here. So what we want to say is, if our tact switch is not pressed, we don't want to count. And if it's pressed, we want to count in order to count how many times it was activated. So let us look at it right here. So if true, we want to count, right? We want to add +1 right here. So we want to increment by +1. And if it is not pressed, we simply don't want to count. So we will pass the values through the shift register as it is. So let us look at what will happen right here. And right here, what we want to create, go to NXG, and right here say count. Perfect. So let us place our counter right here. So I can just wire it, and I can right click and say adapt to source in order to have an integer. Perfect. Let's now count the number of clicks. Let's run the code. Our tact switch is not activated. It's not pressed. We're not counting anything. As soon as we press it, boom. If I press it again, I should by now read 2 instead of 306. So what's happening? As long as the tact switch is being pressed, the counter is increasing. And we don't want that. We want just to count how many times it was clicked. So clearly we have a problem right here that we need to overcome. So how can we do that? It's pretty easy. So let us look at our code again. So what we have right here is the tact switch. And what we need is a clearly defined algorithm. We want to say that between 2 consecutive iterations right here for our tact switch, if it was pressed and it is still being pressed between 2 consecutive iterations, we don't want to count because it means it is still in the same condition. Similarly, if it was not pressed and still in the coming iteration it is still not pressed, also we don't want to count. However, if we have a change in the status between 2 consecutive iterations, which means it's pressed and unpressed, or unpressed and pressed, we need to count. So how do we do that? It's pretty simple. We need a shift register for the Boolean to monitor the Boolean value. So we can initialize this one, this Boolean value right here. And what we want to do is we want to read the state in the state of the tact switch in the current iteration and from the previous iteration. To do so, what we can do is we can gather it through our shift register. So this is our shift register right here. We're reading it and feeding it back here. We're reading it in the current iteration. So we're reading the value of the tact switch status from the previous iteration, and we will compare it to the one in the current iteration. Now what we can do is we can use an AND gate right here and say if these two are true or false. Let's see what we want to do in order to analyze it. So we're saying right here, let's write it right here. We're saying if in the current iteration we have true, which means the tact switch is pressed, and from the previous iteration, so let us write here current versus previous iteration in order to fully understand. So in the current iteration we're reading true, and in the previous one we have true. It means the tact switch has been pressed and it is still being pressed. Nothing has changed. So what we want to read is we need the output to be false. If it is similarly false and false, which means it was unpressed and it is still unpressed or disactivated, we also want to read false. Also, if we have true right here, and false, which means in the current iteration it's true, which means it's pressed, and in the previous iteration it was not pressed, we want to read true right here. And if we have false, the opposite case, which is false, unpressed, and current, unpressed in the current iteration, and it was pressed in the previous iteration, so true, so change of state, we want to read true. Let's see if this will apply right here. Let's say we're pressing it in the current iteration. We're reading true. And in the previous iteration, it was not pressed. If it was not pressed in the previous iteration, what we will read is false. And if in the current one it was, so let's put right here true, just to illustrate it so you can see it in front of you. So true in the current iteration. If it was not pressed, we will read false. We have true and false. What do we expect to read here? We expect an output of true in order to count, because we have a change of state, whether we have true or false, or the opposite, which is true, false, true. We expect to have true. However, we can see that for this and right here, we won't have true. What we will have is false, because I have false and true, or true and false. And for the AND, we need two of the conditions to be true in order to have true. So what we can do is flip one of the inputs right here. So I can insert right here, go to the Boolean palette and flip it. Now if I have true and false, this false will be flipped to true, and then I will have true, true, and it will read true. And if we have false, true right here, we'll have false right here, and here the true will be flipped to false, and we'll have false, false, and then we'll read a true right here. What happens if we have true, true? If we have true and the true right here, one of the true right here will be flipped to false, and then we'll read false, and similarly for the false case. If I have false and false, the false right here will be flipped to true, and we'll read false, and we won't count. So let us go ahead and check if this works reliably. Perfect. So let us run our code, and as you can see now, the count is 0. I press once, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. So now it's working perfectly. Now what I can do, I can activate my tactile switch. Just as an example, I can activate an LED or the embedded LED on the Arduino, which is connected to digital pin 13 through the tact switch. And what we are going to do is we are going to let this tact switch now behave as a push button, as another example. And what we mean by that is the following, as a push button. If we click once, the LED will turn on. If we click twice, it will go off. Then if we click again, once it will turn on, then again off. So we will make programmatically our tact switch behave like a push button. So let us do that. So for our digital channel right here, it's 13 because this is for the embedded LED right here on the Arduino Uno. Perfect. And for our digital value, we will connect it to, as we said, so let us move it a little bit to the side. All right, move this one a little bit also to organize our code. Right. Perfect. So now what we are going to do, we have our counter right here, and we are going to take our counter right here, counter value. And this counter value, we're going to divide it by 2. So I'm going to take it, create a constant, divide it by 2, and we are going to check the remainder. If the remainder is 0, it means we have pressed twice or it's not pressed, we will turn it off. If the remainder is 1, we will turn it on. So let's see. So I can say here, is the remainder equal to 0 in the comparison palette? If the remainder is equal to 0, it was pressed twice, then we will turn it off. Okay, on. So let us look at it right here. I can. And let's visualize it also virtually. So we can just duplicate this one and call it LED. And now we have our perfect. So let us run our code. So now the LED is off. If I press once, the LED is still off. Of course, it will be off, but we can see it right here. Now it's off on the Arduino. If I press once, it's on, off, on. Now, of course, it won't be activated on LabVIEW because we have not connected the LED. So where is it? It's right here, and we want to connect it right here. So let's look at what we have right here. So let us run the code. If we run the code, initially the LED is on. If I press, it's off. If I release, if I click again, on, off, on, off, on. Now there's one minor issue right here. Let's run the code again. It starts with an on. So the LED is initially on, and then I need to turn it off. So in order to do that, I can say right here, replace comparison, and say if it's not equal to 0. So I can flip the conditional terminal. And now if we run the code, we have an LED that is off, and you can see it physically right here and virtually right here. So notice the physical one. So on, off, on, off, on, off. And I can monitor at the same time the number of clicks. And this is it for this tutorial.